Okay, we are going to talk type 1 errors, type 2 errors, and power. Okay, so let's start by saying we own an apple pie company. Okay, and our apple pie company gets shipments of apples that come on a huge truck. Okay, and we have to decide if each big truck that comes in, if we're going to accept that shipment of apples or if we're going to reject it. So we set up a hypothesis test, okay, where P equals 0.8, okay, and the alternative is P is less than 0.8, where P is the true proportion of good apples in the shipment. Okay, so we're hoping for 80% good apples. We're saying we can work with that. Okay, but if we have evidence that it's less than 0.8, we need to reject that shipment of apples. Okay, so we're going to take samples, okay, of 50 apples. Okay, so every time a truck rolls in, we're going to take 50 apples and check them out. Okay, and base our decision on those 50 apples. All right, and we're also going to have a significance level of 0.05. Okay, so first scenario. Okay, scenario 1. Let's say P is 0.8. Okay, so the true proportion of good apples in the shipment is 80%. Okay, it's a shipment that we should definitely accept because it's within our range that we'd be okay with. All right, so we got to think about our sampling distribution. Okay, if this is true, okay, then for our sampling distribution, mu p hat would equal 0.8. Sigma p hat would equal square root of 0.8 times 0.2 over 50, since we're doing samples of size 50. And if you get out your little calculator, that comes out to be to 4 significant digits. That's what we have there. Okay, so what our sampling distribution would look like: mean at 0.8. Okay, our nice normal distribution there, since our central limit theorem is met, right? N times p hat would be 10. N times 1 minus p hat would be 40. Okay, so it would look approximately normal. This is it. So 2 standard deviations away, okay, would put us maybe like about here. Okay, so you have to understand that this is our sampling distribution. There's going to be some sampling variability, okay? And if we happen to get a bad sample such that p hat in the sample is low enough, we would still reject the null hypothesis even though that's true, okay? And in fact, if we get a p-value of 0.05 or lower, we will reject the shipment. We'll reject the null hypothesis when we really shouldn't, okay? And we know that's a type 1 error. Okay, so we know that that's going to happen 5% of the time. Okay, so we can figure out actually what our cutoff is for an acceptable shipment versus an unacceptable shipment. Okay, this z value right here, okay, if we do the inverse norm of 0.05, we get negative 1.645. Okay, so if we get a z value of negative 1.645 or lower, despite the fact that p is 0.8, that might happen once in a while because of sampling variability, and we're going to reject that truck. Excuse me. Okay, so we can even figure out when that would happen. Okay, so when z is p hat minus mu p hat over sigma p hat, or when negative 1.645 is equal to p hat minus 0.8 over that 0.05657. Oops, 57. Okay, and that's going to happen when p hat is 0.7070. Okay, so this 0.7070, if we take a sample of these apples and we get 70.7% or higher good apples, we are going to accept our truckload. Okay, and if it's anything less than that, we are going to reject our truckload. Okay, and again, the really important thing to understand here is that even when P is 0.8, and we should accept it, sometimes just by chance, we're going to grab 50 apples, right, that just aren't that good. Like if 80% are good, there's 20% not good. Okay, it's totally possible that we grab 50 apples and none of them are good. And we say, get rid of this truck, when really we just grabbed all the bad ones for some reason. Okay, it could happen. All right, so this value here is really important. So as owners of our apple pie company, okay, we're not going to like run this test every single time. We've done the math once and we know that that 70.7 is our cutoff. Okay, so that's your first scenario. Okay, the null hypothesis is true. We should accept it. We should take the truckload of apples. 5% of the time, we're going to make a type 1 error and we're going to reject it when we shouldn't have. Okay, and that goes back to your probability of a type 1 error is the same as alpha. Okay, so if we want to reduce the probability of a type 1 error, we reduce alpha. Okay, so reduce the probability of a type 1 by reducing alpha. Okay, all right. Now, scenario 2, this is where we get a little bit more dicey, okay? So scenario 2, okay, P is less than 0.8, okay? It really is less than 80% good apples on the truck, and we should reject the truck. Okay, and the question is, are we going to? Okay. Well, if we go back up to what we decided up here, regardless of if we have taken any sample at all, we know that our cutoff 0.7070. This will cause us to accept the truck. This will cause us to reject the truck. Okay, and then we can even sketch in here. I'm going to use real light green. Okay, this was at 0.8. Okay, so in the green there's our hypothesized sampling distribution. Okay, just so we can kind of see where it falls here. All right, well now in scenario 2, okay, when we're talking about we're getting at this type 2 error in this power, you have to have an alternative that is true. Okay, so the power of a test is always to detect a specific alternative. Okay, so let's say the alternative is p equals 0.65. Okay, so when you're setting up a test and you want to figure out how powerful the test is, you have to pick an alternative that we absolutely have to be able to detect this alternative. Okay, so I want the power of my test to be whatever percent for this specific alternative. Okay, so maybe our specific alternative is, okay, I want 80% good apples. I have to have a test that will that will definitely have a power of 80% maybe to reject it when the truck has 65% bad apples. Okay, so a high power test against this specific alternative. Okay, it's kind of like this is as low as I want to go. Okay, so there's a lot of things that you'd have to consider here as the owner of your apple pie company. It's not all just baking. You got to think a lot about all this stuff. So there's a lot going on behind the scenes. Okay, so let's say this is true. Okay, so P equals 0.65. So then our actual, let's see here, 0.70. So maybe about 0.65. Let me get a different color here for this. Okay. So 0.65 is right here. Okay. So let's say that this is the actual sampling distribution. Okay. Then this 0.70 that we have on there, okay, that on the green curve had a z-score of negative 1.645, okay, actually has a different z-score on the purple curve, right? It would be positive. So on that purple curve, that same z-score, okay, let's see here, would be z of 0.7070 would be 0.7070 minus 0.65 over the square root of 0.65 times 0.35 over 50, which is 0.8443. Okay. All right. So we can figure out the probability that we will accept the truck when we should reject it, right? Again, we're in scenario 2 here. P is 0.65. So let me get out my highlighter here. We're still going to reject the truck, okay, if our sample puts us in this highlighted purple range here. Okay, and that would be a type 2 error. So the probability that z is greater than 0.8443 is 0. Oh, I gotta grab my calculator here. 0.1992. Okay, that's this area here. 0.1992. Okay, I'm going to go ahead and get my type 1 error shaded in on there too, right here. And technically it goes on forever. Okay, that'd be my type 1 error. That's 0.05. Okay, so there's your 2 errors. In the purple, that's a probability of a type 2 error. Okay, where I should reject the truck, but my sample of 50 is above that threshold where I'm going to just go ahead and accept it. Okay. And then my 0.05, that's the type 1 error that we did above. And I could also shade in this area here. So 1 minus the purple area. Okay. That is the power. Okay. That's 0.8008. Okay. So the probability that z is less than 0.7070, that's a probability, or I'm sorry, that's the power of the test, which is 0.8008. Okay. And in general, it just so happens that we look for power to be around 80%. Okay. So this all worked out to have kind of an ideal power. Okay. We can always, depending on the scenario though, too, say that we want a higher power. Okay. So we want that blue area to be bigger, which would mean the purple area is smaller. So we're going to let's write this here. Okay. So we talked above here, how can I reduce the probability of a type 1 error? I can reduce alpha. Okay. There's more ways to reduce the probability of a type 2 error. Okay. So if I want to reduce the probability of a type 2 error, which in turn increases the power. It just has to because they add up to 1. So if I reduce the probability of type 2 error, that scale adjusts and then I increase the power. Okay. So if I want that purple to be smaller, okay, that cutoff region, one thing I can do is I can shift that whole purple curve further to the left. Okay. If I shift that whole purple curve to the left, then the area that's getting cut off is smaller, right? And then the blue area gets bigger. Okay. So I can choose an alternative farther away. Okay. So maybe I don't have strong power to detect P equals point, let's see, like 0.68 would be really hard to detect. Okay. But 0.6, it would be pretty easy to detect that. Okay. The farther you get from kind of that hypothesized value, the easier it is for you to detect that that's just the null hypothesis is not true. Okay. So we can choose an alternative farther away. We can also get that area smaller by having a bigger sample size. Okay, because what that does, if our sample size is bigger, that gives us less variability on our normal curve there. It shifts the peak up and the tails in. Okay, so the peak would be at the same, whereas if you choose the alternative farther away, it's basically the same size, but just like shifted down. But if I do a bigger sample size, the peak gets bigger, the tails get smaller, so that purple area gets smaller and the blue area gets bigger. Okay, and that should make sense, right? We always know bigger sample sizes are always better. Okay, my third option is I can shift where that dashed blue line is. Okay, I could shift that dashed blue line to be to the right more. All right, and what I would have to do for that is increase alpha. Okay. If I want to shift that blue dashed line to the right, then that green area gets bigger and the purple area gets smaller. Okay. And that green area, remember, is alpha. So alpha gets bigger. Okay. So that also increases the probability of a type 1. Type 1. Okay. So that's where all the calculations come from. Okay, which you're never going to have to do, but it kind of helps you to understand what those 3 areas are. Okay, again, the purple area is the probability of a type 2 error, the blue area is the power, the green area is the probability of a type 1 error.